Thanks for gathering around the virtual telescope with me again. Today, we've got several articles that I'm going to cover. Just a couple today, did a couple, one yesterday, just trying to get them in as I can. We got a new puppy this week, and my time is really, a lot of my time has been taken up with that new puppy. Anyway, the sun's secret smoke rings, how plasma vortexes survive the solar wind. So as amateur astronomers, a lot of us love observing our nearest star, the sun. We spend countless hours at the eyepiece looking through H-alpha filters or solar telescopes. Some use electronic telescopes like the C-Star. That's what I do. I do the C-Star and my solar telescope, which is totally safe to look at. Make sure you never look at the sun unless you have the proper equipment. You don't want to damage or your eyes or go blind. Always put that there. Anyway, as we look, I don't know about a lot of people, but I'm sometimes mesmerized by the delicate flames of the solar prominences that I can see coming off the sun. It's incredible to think that these solar prominences are dancing, snapping, and occasionally hurling into space as coronal mass ejections, CMEs. But what happens to the material once it leaves the sun's immediate vicinity? A groundbreaking new study led by Shadia Rifai Habbal and her team reveals that the sun is blowing vortex rings, essentially magnetic smoke rings that travel much further than we ever realized. This is the video. It's embedded over at EadsyAstronomy. It's 7 seconds. I'm just going to play it and watch this region over here. It's just incredible. Look at that erupt. Okay? And then as it does that, you can see down below this image, which is the top image, and it kind of explains what we're looking at here. Scientists have long known about the prominence corona transition region, PCTR. This is the frontier where the cool, dense plasma of a prominence meets the scorching thin atmosphere of the corona. In this turbulent zone, we see plasma instabilities, essentially chaotic movements of gas. One of the most elusive structures in this zone are vortex rings. Imagine a ring of smoke blown out by Bilbo Baggins in the Fellowship of the Ring, and I put a link here, and you can actually go there and see it. It's in the Fellowship of the Ring where Bilbo blows the smoke ring out, and you can see the smoke ring comes out. Anyway, the smoke ring holds its shape because the air rotates around itself. On the sun, these rings are made of plasma and are held together by magnetic fields. Until now, we didn't know that these rings, if these rings simply evaporated or if they would survive the long trek into interplanetary space. So here in this image, and it's the image at the beginning, prominence eruption video, and the video is above, which I showed, during the flare of June 7th, 2011, as captured by SDO AIA, shown as composite images from 304, 171, and 211A channels in the SDO AIA. The composite was processed using the NEF algorithm by M. Druckmiller, 2013. The white arrows, which you can see right here and right here, point to twirling filaments in the prominence. The orange arrows, or yellowish arrows, whatever you want to call them, point to the very faint envelope of the ensuing CME. This example shows the complexity of the twirling motion of the prominences as it erupted between the opposite magnetic polarities of the sunspots underlying the active region. The high-tech backyard setup. To solve this, researchers used a combination of two very distinct types of cameras. The total solar eclipse TSE images. During an eclipse, the moon acts as a natural chronograph, allowing us to see the corona in incredible detail, starting right from the sun's edge, the limb, so to speak. And then WHISPER, Wide Field Imager for Parker Solar Probe. This is a camera on the Parker Solar Probe, which is currently touching the sun. It takes images from inside the solar atmosphere. By stitching these together, the team created a continuous view of the sun's atmosphere from the surface out to more than 10 solar radii. It's about 4.3 million miles. So key findings for your next solar party from this article. If you're talking to your astronomy club or doing outreach about solar observing, here are some big takeaways. Vortex rings are survivors. The study found that these magnetic rings don't just dissipate or melt away, they actually expand and travel out into the solar system. The speed connection, the researchers tracked these rings and found they move at an average speed of about 249 kilometers a second, roughly 557,000 miles per hour. Interesting, this matches the acceleration profile of the solar wind. This suggests that these vortexes are a key part of how the solar wind is fed and shaped. A key in the growth, the rings grow at different rates. Below 1.5 solar radii, very close to the sun, they expand slowly. Once they pass about 3 solar radii, they hit their stride and expand much faster. This tells us something fundamental about how the sun's magnetic grip weakens as you move farther out. Why does that matter to us? For those of us who love observing the sun, the research adds a new layer of wonder to what we see through the telescope. Those prominences that we see in ourselves or our own telescopes or in reviewing high-resolution images of prominences aren't just random noise. They are the birth complex of magnetic structures that might eventually sweep past Earth. The study proves that the chaos we see at the edge of the prominence is actually the source of organized structures that help define the environment of our entire solar system. I've put down here, just really quickly, a terminology cheat sheet for amateurs, what plasma instabilities are, Kelvin-Helmholtz waves, white light images, and solar radii, which is a unit of distance. 1 rs is the radius of the sun. So if something is at 10 rs, it's 10 times the sun radius away from the center. Anyway, you can look over that. Again, I hope you found this interesting. I found it just wonderful to take a look at. Thanks for listening. We'll catch you next time.